Good afternoon. Okay, another rainy day. So we talked about equilibria. I'm getting help. We talked about equilibria the last time, and we looked at the equilibrium A moles of A plus B moles of B. These are our reactants. Give C moles of C plus D moles of D. These are our products. And we looked at all kinds of equilibria. We looked at the liquid-gas equilibrium. That's the boiling of water. It's a liquid-gas equilibrium. And we also looked at the pure gas equilibrium, the dimerization of nitrous oxide to N2O4. Then we looked at an aqueous equilibrium where we had acetic acid in water, and this gives this proton to the H2O molecule, forms H3O plus. That means it becomes acidic, and the acetate dissociates. And then we had a heterogeneous equilibrium where we had an aqueous and a solid phase. Silver and chloride ions were in equilibrium with silver chloride. I'm glad that you guys are talking, because this morning the people were essentially not here. They were here, but I don't know, there was nothing. There was no sound, nothing came from them. So at least I know that you're here while you are yakking with each other. That's which is a good thing. So as long as you get what I say, it's fine. So the mass of law, the law of mass action is nothing but a quotient. That's the quotient you form between the product and the reactants. So we say the reaction quotient Q is the concentration of product C to the C's power, so that's the moles, the number of moles goes at the exponent here, and then times the concentration of product D to the D's power, that's again here, that's the number of moles, divided in the denominator, the concentration of A to the A's power, divided by the concentration of B to the B's power. And this is Q. And we talked about Q, that we are at standard conditions. You calculate, for example, these enthalpies at standard, the changes of enthalpies for a reaction, you calculate at standard conditions. And that means that everything, if you have gases, the products and the reactants are all at 1 atmosphere. Okay? This is how we calculate this. This is definitely not equilibrium. That's just very much a disequilibrium, because I hardly have ever seen a reaction where the products and the reactants and the products are all at 1 atmosphere. Doesn't happen really, okay? So this would be the reaction quotient you can formulate for this. What would be the reaction quotient, for example, if you have a gas reaction where you have reactants go to products and everything is at 1 atmosphere? What would be the number for the quotient? What would be the quotient? 1, exactly, 1. And if you have everything at 1 mole here, then this would be also 1. This would be at standard condition. It has nothing to do with equilibrium. You can put everything at 1 atmosphere, and then you wait till it equilibrates, okay? And the pressures will change, or the concentrations will change, till it is in equilibrium. And the equilibrium is a fixed constant at a fixed temperature. At each temperature, there's only 1 constant for any specific reaction, and it will change that equilibrium, that reaction quotient, the concentration of the reactants and the reactants and the products, until it has reached K, that number. Okay? And so if you add, for example, some more of B here, then it will make more products again until it had reached that quotient again, that equilibrium constant, which is also a quotient, but it's a very specific quotient. So we talked then how we formulate these quotients, and we used that example, liquid water in equilibrium with gaseous water, okay? At what temperature is liquid water in equilibrium with gaseous water, with steam? At 25 degrees Celsius? Yeah, that could be possible at 20. What would be then the equilibrium pressure? The vapor pressure above at 25 degrees Celsius? 0.003 what? Atmospheres. Okay? Now if I go at 100 degrees Celsius, this is the boiling temperature of water, what would be the vapor pressure above there? Would be 1 atmosphere, exactly. And so you can now calculate this. Let's say we do this for the boiling of water. We take the concentration of the gaseous water. The concentration of the gaseous water is the partial pressure of H2O, divided by the concentration of the liquid water. We would have to divide this here by the concentration of H2O. But pure phases we have defined, pure phases we set to 1. We ignore them, we set them to 1. If you have pure solids or pure liquids, then you set this to 1, okay? So you have that 1 we don't write here, so that's just the partial pressure of water. And in equilibrium, it's actually the partial pressure, the vaporization pressure, the pressure it has at the vaporization temperature. And this is 1 atmosphere in this case. And this would be K, okay? You can Q is at any temperature, and so it has to have a certain value to be K, okay? Then it's an equilibrium. As you so rightfully said, the pressure is 1 atmosphere at boiling point of water at our standard conditions here, okay? Now if you go, of course, it will be different, the boiling point of water, if you go higher up in pressure, but that's a different story. Now you also could write that reaction in the opposite way. You say, okay, H2O gas is in equilibrium with liquid water, so steam is in equilibrium with liquid water. So now I could also take, this would be now my product, okay, and this I set to 1, and then I have to divide it by the reactant. I have to divide by the partial pressure of H2O, which would be a new constant and a very different constant because the reciprocal. It's 1 over it, okay? And so what this means is, if you ever look at any equilibrium constants in a book, there's a number there, you need to look, how did they write that reaction? What did they define on the left side and what is on the right side? And it's always right side over left side, okay? So that's very important. Just not only look up the number, but figure out how they write that equation. That's a very, very important issue. So, and then we talked a little bit, no, quite a bit actually, about how equilibrium can reach. I mean, reaching equilibrium is essentially, it can go very fast or can go very slow. But we don't care if it goes fast or slow. We're looking at it in equilibrium. We don't care how it got there, okay? So that would be kinetics. You do this in next semester if you ever go to 1B, okay? So you do kinetics. We don't do kinetics here. So there was, for example, that if I have the timeline here on the x-axis and I have the concentration on the y-axis, that means I could have here then a reaction which slowly proceeds till it finally gets to equilibrium. See that? Or I could have that clock reaction, nothing happened for a while, and then suddenly the reaction proceeded and went into equilibrium, okay? And then we had several different clocks. We had one rather fast, so this was rather short that time. Then we had excuse me. You're laughing when I'm getting nearly choking to death here? All right. All right. So this was the second time we had it extended further and then went up and went over, okay? And the third one was even longer and then went up and over, right? So that's a different time it took for the reaction to get into equilibrium. And then we had this oscillatory reaction where we had blue going into gold and gold going back to blue, back and forth. So it was overshooting the equilibrium, undershooting the equilibrium, overshooting, undershooting, and the frequency got much smaller than at the very end till it has reached equilibrium. So that was our Go-Bears demonstration of blue and gold. And then you have this chaotic reaction where there's no way that we mathematically can express the way how it goes from disequilibrium into equilibrium. But at the end, it will reach equilibrium. So today we're going to talk a little bit more about equilibria. We're looking into a couple of different equilibria, and we also talk about Le Chatelier's principle and the synthesis of ammonia and why it's so important, that synthesis. So if you look at this equation here, this equation is the dimerization of NO2 to N2O4. So if you are, and all of you are smart, so not if you are smart, you are smart, you should be knowing here if this is an exothermic or an endothermic reaction. You're looking from this here, you go from here to that. Is that exothermic or endothermic? What do you think? Endothermic. Why is that? Takes energy to make bonds. Are you kidding me? It takes energy to make bonds? Yeah, let's look at the energy only. Let's not look at the entropy. Let's look at the energy, just at the energy. If you look at this energy-wise, only at the energy, not the entropy, what would you say? Would it be exothermic or endothermic? Correct yourself. What do you have here? Why is that exothermic? You're right. Why is it exothermic? You do what? Energy is released when bonds are made. Exactly. You have 2 NO2, you're making 1 N2O4. So you're forming new bonds. You're releasing energy. So this would be with the entropy, you're right, but let's look at the enthalpy at this point. Yeah? From the enthalpy side, we can say, this must be exothermic. And sure enough, it's minus 57.2 kilojoules per mole. Please get this in your head. If you form bonds, you release energy. If you break bonds, you need energy to break them. All right? I don't want to see that mistake. I don't want anybody to I don't want to see anybody make that mistake. See how upset I am? Okay. So at 25 degrees, that K is about 7. So it always will do anything to reach that K of 7 at 25 degrees to get into equilibrium. So the Q is now, this is our product, obviously. We wrote it this way. This is our product. So it's the partial pressure of N2O4 divided by the partial pressure of NO2. And I need to square it because I have 2 moles. All right? So this is the partial pressure, this is this quotient now, and this is Q. What is this at standard conditions? What is the number at standard conditions? Come on. 1, good. But at equilibrium it's not 1, it's 6.8. So obviously it goes into that direction here. And this is at equilibrium 6.8. Of course, at 25 degrees Celsius. If you have another temperature, that has a different number. But it is a constant. At the constant, it depends on the temperature. So let me see. You have here this La air in here, okay? And so this is NO2 and N2O4. That NO2 is brown, that N2O4 is colorless, but the brown overshadows everything in that equilibrium, okay? So you can't see colorless if you have brown in there. So you have this mixture here. This is an equilibrium. This is the equilibrium I just shown you here. This is that equilibrium. And it's an equilibrium, and I have here the same arrangement, and here I have a valve, okay? So now I quickly open that valve, and obviously the gas goes over here. It is not in equilibrium at that point when I do that, all right? I got it out of equilibrium because I gave it suddenly more space. Now the question I'm asking you, from this point, I just opened it and it's not in equilibrium. Now it tries to go back into equilibrium. What will the color intensity do? Will it increase? That means increase, it will make more NO2. Will it stay the same? or will it decrease? That means it would make more N2O4, okay? So you open that valve, and now you start looking. It's not in equilibrium because we disturbed the equilibrium, and now I want to know what will happen, what will it do to get back into equilibrium? Think about it and give me your answer, please. What is it? No. 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 You need to think. We brought it out of equilibrium, and we want it to get back into equilibrium, and it has to do something in order to get back into equilibrium. Let's see, maybe the reaction is here. Yeah. Right there. Now we're talking. Okay. It did decrease, the color intensity did decrease when I brought it into disequilibrium. Suddenly it has all this more space, okay? And so it fills that space, but it has to go back into equilibrium. So what will it do? Why don't you think about this maybe as a change of volume? You have the volume change, so maybe you write that equation, where is that quotient equation, and say if you now have double the volume, what happens to the pressure and what happens to K? Okay? Why don't you discuss this with each other, please, and try to at least figure out what I'm trying to go at. This is brown here, and this is colorless.
And they're both in the...
Yeah, they're both in there. And I tried to tell you that you can't see the colorless because the brown sort of dominates the system in terms of color. Wow, 257 people here. That's great. Must be raining outside. Must be midterm coming up. Okay. There's a midterm coming up? Not funny, huh? So 113 of you say it increases. 185 said, I really don't know what he wants from me. And 163, 85 say I stays the same. And 63 say it will decrease, okay? So let's look at it this way. So if it would go into this direction over here, would the color increase or decrease if I make more of NO2? the color would increase. If I make more of N2O4, the color would decrease, wouldn't it be? If I don't do anything, the color would stay the same, all right? So we are so far so good. So there it is. Now it has suddenly double the volume, isn't that right? The gas has suddenly double the volume, and it's not in equilibrium anymore. So at the beginning, we have this here. So this is our initial condition here. P is N2O4 Q is the partial pressure of N2O4 divided by the partial pressure squared of NO2, okay? And in equilibrium, Q equals K, all right? So that was about 6.8 in equilibrium. Now, let's just say we have doubled the volume. What did this do to the partial pressure? What does it do to this partial pressure? Decreases to what? 1/2, exactly. So this 1/2 this partial pressure, 1/2 this partial pressure squared. And what does, if this here, so we have to, the volume is twice, so how big is that constant then? Double, excellent, who said that? Very good. It's twice the constant. Is that equilibrium? No, isn't equilibrium. What does it say? If this is twice the constant, so we have too much up here in the numerator. All right? So we need to get rid of N2O4 and make NO2. So it will push it into the direction of the reactant, or to the left, because we need to get to K again, not to 2K. It has to get the value of K, which is 6.8. And with this, it will increase because we're making this here, and this will become browner than before until it reaches the same color than it had before. Okay? All right, that was not easy. So we can also look at this at the famous Le Chatelier's principle. That means if, like you get pushed, you push back. Okay? Don't take it. But the equilibrium is the same thing. You do something to equilibrium, the equilibrium tries to get, no, I want to be in equilibrium. Goes back, all right? So for example, you take away NO2, what will it do? It will make more till it's back in equilibrium because the concentration is out of whack, so to speak, okay? It's not, if you take this away here, that means you will get smaller than K. So you need to make more of this stuff, all right? And so this is the possibility that equilibria do. Or you can, if you add here some more NO2, what will it do? It will equilibrate till Q equals K, till it's back in equilibrium. So the Le Chatelier's principle says that a system in equilibrium, if you stress that system, that it will react in a direction that tends to reduce the stress. So that sounds very philosophical. So it will try to get back into equilibrium. That's the whole point of it, all right? So let's see. We had our gas, this N2, these are the NO2, and this is the N2O4. They were in equilibrium here. Q was K, and K was 6.8, something like this. And now we increase the volume, and we are not in equilibrium. We're absolutely not in equilibrium. At this point, we are not in equilibrium. We have to go back to equilibrium. We got to give it some time to get into equilibrium. Now we have double the space, and this is not in equilibrium. Okay? So what do we do? Q is larger than K. Q is larger than K. That means this here is too large, the partial pressure of N2O4. So we're going to take some of these N2O4, and we change the partial pressure to get the partial pressure back up, and change Q in order to get Q equals K again in that volume. And this, now K is again, we haven't changed the temperature, we just changed the volume, and K is now 6.8 again. All right? Good. Le Chatelier's principle, and we're going to deal with this a little bit more today, but Le Chatelier's principle. Perfect example for Le Chatelier's principle. Anybody can tell me what hem or hemoglobin does in your body? What is the function of hemoglobin? It carries oxygen. What else does it carry? Iron, yeah. But it also carries away, it brings the oxygen to the reaction centers in the body where it's needed, but it also carries away your reaction products, which is CO2, okay? And the CO2, this exchange happens in your lungs. You breathe in, the hem catches the oxygen, sequesters it or chelates it, and then it brings it to where it reacts, and it picks up the CO2 and gets it back to the lungs, and that's what you breathe out. Now, it's not very good in distinguishing between carbon monoxide and carbon dioxide. So if somebody breathes carbon monoxide for any particular reason, you actually suffocate, and you don't know that you suffocate. You are breathing still, but you don't get any oxygen because it's blocked. So if, for example, somebody has a faulty heater and the carbon monoxide is not properly vented, you die actually without knowing it, all right? There's other ways where people use that for other reasons also. Anyhow, so you find somebody, you're a medical doctor now, you find somebody, well, let's see, first what is an emergency technician, okay? You find somebody and they tell you that this person obviously is unconscious and you see there's a heater there, and so you assume must be maybe carbon monoxide poisoning. The first thing is you open the window, okay, that you don't go down. And the second thing is you could do the following thing. You try to cool off that person. You put them in an ice bath in the tub there, or you take a needle and try to remove all the hem from him, okay? Or her. That might be also a possibility. Or the third possibility, you increase the partial pressure of oxygen in his blood, so you let him breathe oxygen. So what do you think would be, just from the physics, from the equilibrium conditions, what would be the best way to treat this person? One is A, B, or C. 1, 2, or 3. Why don't you think about this? So that person would not feel very healthy here. I think it wouldn't even stand up anymore. All righty, 267, we are multiplying. That's wonderful. Is anybody of you watching this owl, or this hasn't come to you yet? No, I'll tell you this later, not today, I don't have enough time. There's an owl on the web, which has 4 owlets, and I don't know, every time there's 15,000 people watching that. And you can see how the owl feeds the young ones, and the mate brings in, like the other day, he brought in a whole rabbit. They shut the feed down quickly for a while, because there are children watching. Anyhow, so that is a good, there seem to be quite a few good doctors here already. Okay, you increase the partial pressure. Le Chatelier's principle, okay, so these are your products, and oxygen is a product, but I need to get over here, so I need to increase that pressure here of oxygen to push that reaction in the opposite direction, and with this, you go here, you increase the oxygen pressure here, let the person breathe oxygen, and you will then increase the oxygen with on the hemoglobin and decrease the carbon monoxide on it, and you might save that person. Okay? Alrighty. There are people dying, actually, quite a few per year, every year, on that. So let's think about this here. So we established that NO2 gas to N2O4. This is what this is here. Who is from LA? Home. Home. Who is from Beijing? Nobody? Home. Okay. So, I'm just kidding, okay? So this is a dynamic equilibrium. There's NO2 is brown and N2O4 is colorless. So there is colorless N2O4 in there, but you can't see it because it is overpowered by the brown color, all right? So we have established that this is obviously an exothermic reaction, okay? An exothermic reaction. What happens to the color intensity if I raise the temperature and let it come back into equilibrium? Will the color intensity increase, stay the same, or decrease? That means increase, it gets browner, or it gets lighter if I increase the temperature. Why don't you think about this and give me your answer? That's again a case of Le Chatelier's principle, but this time we do it with temperature. So we don't raise the temperature so much that there's a pressure change, okay? Let's ignore the pressure change. The pressure change, we raise it by 20 degrees. The pressure change difference is very small. We say there's no pressure change at this point. So this effect will dominate. It's not the pressure change. So ignore the pressure change. You know this is exothermic, okay? You could write an E either here, probably plus E here, okay? It's exothermic. Okay, to be perfect balance, huh? It's just equilibrium. It's a perfect. I need to get you though into one direction, so I need to give you a little Le Chatelier's principle. I need a new battery for that microphone, please. Okay, now think of it. So this we said it's exothermic. Okay, so if it would be endothermic, I would write E plus this here. If it's exothermic, I could write plus E here. Okay, plus E. Now with this, heat becomes a product, okay? And we're heating it up more. Why don't you think about this and discuss it with each other, please? Just have a discussion. So are we coming? I said you could look at it as heat as a product. And you put in more heat, obviously. Yes, ladies and gentlemen. Okay. Yeah, you got it. You got it. So this is how you look at this. You say heat is a product. So if I increase the temperature, I'm pushing it over here. And with this I make more NO2, and with this the partial pressure of NO2 goes up and the color will increase. Now why don't we do this here? I'm going to do a little experiment. I will subject that air to, there's one more thing I would like to talk to you about. So there is, if it's exothermic, that means it decreases, K decreases as a function of temperature. If it's endothermic, K increases as a function of temperature. Okay, you would put if it's endothermic, you would put the heat here, and the heat would be product. So let's do that quickly. I have here two, why don't we do it with one first here? So I said this is, can you see it up there? Yeah, very nice. A little fuzzy, but okay. So I'm going to, you see the color? I'm going to heat this up here. So it should get darker, shouldn't it? Hope it's warm enough. Come on. Equilibrium is exciting, isn't it? You see the difference? Okay. Now what happens if I cool this off? Gets lighter, hopefully. Because I'm pushing it in the other direction. I take heat away, and so it makes more product. See the difference? Got lighter. Not quite as light as we would like it, but it's lighter. So I could do this for a longer time, but somebody would have to hold it. Okay, now let's talk about nitrogen supply. Nitrogen is important to us, and we can't get it into our body because we need to make proteins from amino acids and all kinds of we need nitrogen for all kinds of compounds in our body. And 80% of this is nitrogen in the air here. But I breathe it in, that's not how we get our nitrogen in the body. We get it through our food. And the food, usually plants, it's okay, let's give it another try. He's back. So what you do, you put fertilizer. This is fertilizer. Ammonia is fertilizer. That's a huge, huge industry, which is also very much a CO2 producing, okay? So if you would eat, never mind. So this is NH3. This is the form you put on in the fields and as fertilizer, and then the plants grow and they incorporate it in the plants, and then we can eat it and we get it into our body. So this is an exothermic reaction. It's an exothermic reaction, but you need to have, this is gas here and this is gas. So that means if you heat that, then it goes in this direction. But if you put pressure on it, then it will go in this direction. So this is done usually on a catalyst, and this was discovered by Fritz Haber in 1910, and shortly after, they made a big process out of this, and Harvard became filthy rich, actually, because he got 1 penny per pound of ammonia that was produced. So he had this patent and got 1 penny per pound. It was a fortune at this time of the history in 1910. So now, if you remember, how many billion did I say? 30 million pounds are produced. Let's see, what is it? 30 billion tons per year, okay? In the US alone, okay? So that makes a lot of CO2, and that's not so good. So what else could you use that for? Say it. It was in 1914 when they made it a big process. What happened in 1914 in the world? World War I. Of course, these are explosives. These guys at Oklahoma City, they loaded a van full of fertilizer and blew it up. And it took out nearly all the building, killed all these innocent people. And so people become very suspicious if you buy large amounts of fertilizer in the store, okay? They will report you, hopefully. And so, of course, the war makes the process go, all right? All the invention is, and you make a lot of money if you get involved in wars. If you're not the soldier, then it's a different story. But the people, that's why we have so many wars, essentially, because lots of people make lots of money in that, okay? And it's very unfortunate, but it's not part of the subject of this lecture here. So what we do is, this is very slow at 25 degrees. We need to put in temperature, and it's exothermic. So at high temperature, that means we have a low K, so we need to raise the partial pressure, and there's this trade-off between the temperature and the partial pressure of these gases here. It's at 500 degrees Celsius and 200 atmosphere. This process is done, the Haber-Bosch synthesis of ammonia from nitrogen and hydrogen gas. And it's done with a catalyst, of course, to lower the activation barrier. So you can also have multiple equilibria, where you can have A goes to B, and it has an enthalpy of reaction, and it has an equilibrium constant. And then you can have B goes to C, has another enthalpy of reaction, and an equilibrium constant. And then you have A goes to C, that has another enthalpy of reaction, and yet again another equilibrium constant. So now you could write the equation for that, or the equilibrium constant for that. What would that be? That would be C, concentration of C over A, okay? Now, what could you write here? C is C over B, and B is B over A, okay? So that K3 obviously is what? These two constants, and you multiply them, because these are products here, you multiply them, so it's K1 times K2. This is how you can calculate that to get to this here, and it's a perfect Hess cycle, essentially. And so the delta H3 would be delta H1 plus delta H2 gives you delta H3. We derived this from here, okay? So this is how I deal with multiple equilibrium. Now let's look at the multiple equilibrium, and let's not get fooled, okay? You have this molecule here, okay? It has 1, 2, 3, 4 double bonds. And you make this molecule, and then you make this molecule, which obviously looks like this here, okay? 1, 2, 3, 4 double bonds, right? So now you can calculate that. I show you how to do that. I have shown you how to do this. You can calculate an equilibrium constant. Now I'm asking you, how does this equilibrium constant depend on the temperature? Is it goes down with increasing temperature, stays the same, or increases with temperature? You don't need any numbers. All you need to do is think. That's what they always say. All right, why don't you think and give me an answer? Who would have thunk? So what did I just derive? Delta H3 was what? So what is delta H1, obviously? Think about your bonds. Another near equilibrium here. That looks to me, isn't that like a Hess process cycle? Hess cycle? So this is your initial state, and this is your final state. Okay? Initial state, final state. You're only interested in the initial and final state. You're not interested in the things in between. So what happened here in terms of bonds? You had to break those bonds, and then you had to make them. So the energy for this here is obviously breaking bonds needs energy, okay? And making bond, you gain energy. What's the magnitude of the energy? Why don't you think about this and give me your answer? Discuss it with each other, please. He speaks in riddles, huh? I told you, equilibrium was not that exciting. Not much happens. You want to get out of equilibrium. Alrighty, everybody's in? Everybody click in, please. Some of them have diffused off already. All right. Let's see what it is. Display. Yes! Of course, there's no heat flowing in or out, okay? You break the bonds, you immediately make them again. With this, it's independent of the temperature. And delta H1 plus delta H2 is 0. That goes from A to C, that the K is independent of the temperature, okay? Alrighty. With this, I see you on Wednesday.